This is the main lecture video for the use case titled Robot Workcell Reconfiguration. This video will present how our TRINITY solution contributes to agile manufacturing, what are the benefits of the presented solution, potential sectors that would benefit from our solution for robot workcell reconfiguration, and what kind of investments are required. The developed robot workcell is a reconfigurable manufacturing system suitable not only for large production lines, but also for low-volume, high-diversity production. The main innovative component of the workcell are modular and largely passive hardware components. As the robot workcell already contains an active component, a robot, it can be used to reconfigure the rest of the robot's workspace. Thus, hardware components with passive degrees of freedom can be manipulated by robot and moved to a configuration suitable for the desired task. They are a more affordable option compared to high-cost active solutions. Besides fully automated reconfiguration, the cell also supports manual reconfiguration when full automation is not feasible. Other crucial components of the workcell are new hardware design method based on 3D printing, a software backbone based on ROS, which provides modularity of all software components, fast programming of production tasks through manual robot guidance, and support for quick workcell reconfiguration by manipulating and exchanging the available hardware components facilitated by a digital twin. The main benefits of the reconfigurable robot workcell for the user include quicker setup times for new production tasks and automated or partially automated reconfiguration from one production task to another. New production tasks can typically be set up in 2 to 4 days if no new hardware is required, or 2 to 4 weeks if hardware development is necessary. On the other hand, many reconfiguration processes can be performed fully automatically in a matter of minutes. If reconfiguration requires manual intervention to, for example, exchange hardware elements, the reconfiguration can be usually accomplished in tens of minutes due to the plug-and-produce connectivity included in the workcell and supported both in hardware and software. If new hardware is necessary, the setup times usually increase. The system, however, also supports such cases through the modular design of components that often need to be adapted. This includes exchangeable gripper fingers, exchangeable fixtures, clamps, and exchangeable screw bits, which can be quickly manufactured using 3D printing technologies without the need to replace the rest of the required hardware. The developed workcell can be used in any sector that requires automated assembly of a variety of products that change frequently. The potential sectors of application are listed here. While the proposed reconfigurable workcell was used and evaluated in multiple areas, let's look at an example from the automotive industry. The cell was evaluated on an assembly of various automotive light housings from a family of products. 3 passive fixtures were used to reconfigure the cell for different light housings. To accommodate for various tasks that needed to be done, a tool, finger, and screw bit exchange system was used. Plug-and-produce connectors enabled the exchange of models and trolleys and further enhanced the agility of production needed for this case. A number of hardware components can be included in the workcell. A specific task would only require a subset of these components, so the list varies from case to case. The full reconfigurable workcell includes the listed hardware components. Let's point out the components that were developed by us with affordable reconfiguration in mind. Passive reconfigurable fixtures were based on Stewart platforms. They enable robot-aided automatic reconfiguration of fixtures to accommodate varying objects. The software for automatic positioning is also provided. To expand the robot's workspace without the need for expensive active linear rails, a passive one was developed. Similar to fixtures, the robot itself moves its base to a new position. The same approach was implemented with a passive rotary table. Instead of actuated rotation, the robot rotates the table when the brakes are released. To enhance the modularity of the cell, a plug-and-produce connector was designed. It enables exchange of various cell models, trolleys, or tables. It provides all the necessary connections. They are also used on modular elements, which can be used to construct or reconfigure a cell in a modular, fast, and easy way. The current components, including robots, can be exchanged with new ones if required by the application. A note on the software side. The workcell control and sensor processing system is based on ROS. It is composed of a number of ROS nodes that provide all the required functionality to the workcell. A new gazebo-based simulator is currently under development. This proposed TRINITY solution can improve the agility of the manufacturing process by reducing the setup times for new production tasks and provide automated or partially automated reconfiguration from one production task to another. Modular and largely passive hardware components enable reconfiguration at lower costs compared to active solutions. The two modules connected to the solution presented in this use case are optimal locations and postures of reconfigurable fixtures and ROS peripheral interface. When deploying a reconfigurable fixturing system to mount a set of different workpieces, it is necessary to determine optimal location and postures of the hardware elements from which a fixturing system is constructed. This model provides an optimization procedure for the determination of optimal layouts for fixturing systems built from Stuart platforms. The second related model provides ROS interface to pre-existing peripheral elements that lacked ROS compatibility. It acts as a proxy between the standard periphery connections and the ROS system. It allows users to quickly integrate existing cell periphery into the ROS-based software. It can be customized to meet the needs of different production system peripheral equipment in terms of shape, size, and connectivity. If you are interested and would like to find out more, see the training material describing the related modules in more detail. Thank you for watching this TRINITY use case introduction.